Hello AP Chemistry and welcome to Chapter 17, 17.1, which opens with the common ion effect, which we've kind of already talked about, right? We talked about it a little bit back in the equilibrium chapter. We talked about it a little bit when we looked at that graph of the percent ionization of acetic acid as the molarity changes, right? Because that is also the same sort of thing, right? But the actual wording for the common ion effect says this, right? So when a solution contains both a weak electrolyte, oh, look here, we have a weak electrolyte, and a strong electrolyte, right? With a shared ion, the weak electrolyte ionizes less than predicted by K, right? So if we think about what that means, that's like saying we took some acetic acid, right? And to that aqueous solution of acetic acid, we added some, for example, this, right? So if we added some sodium acetate to an aqueous solution of acetic acid, what that really means is we are increasing the amount of acetate ion, right? Which if we think about what Le Chat says, right, that system at equilibrium will now shift in that direction, right? Meaning that less of that acetic acid will dissociate than is predicted by its Ka value, right? Likewise, for example, if we had a solution of ammonia, right, which is also a weak electrolyte, because our weak electrolytes are, right, weak acids and weak bases, right? So if we had a solution of aqueous NH3, and to it we added some, for example, ammonium chloride, right? The addition of that ammonium ion, same principle, right? It's going to shift the equilibrium in that direction, right? Less of that ammonia is going to interact with the water than is predicted by the Kb value for ammonia. Yes? Good? All right. Now, that's key because that plays into how we do this math here, right? So this says we're going to calculate the pH of a solution containing this concentration of nitrous acid, right? And this concentration of nitrite. Now, obviously, if we think about what that means, right, if we were going to write nitrous acid plus water does this and forms hydronium and some nitrite, right? It could get super complicated, right? If we were trying to deal with what happens to the dissociation of nitrous acid, right? But the point is that based on this, right, what this says, right, is that if we have this ion in solution, this dissociates less, right? So much less, in fact, that we don't need to worry about how much dissociates with respect to the concentration of added ion, yes? So when we look at this, right, this concentration is 0.085 molar, right? This is irrelevant, right? And it says that this concentration is 0.1 molar, right? And we're going to say that's 0 to begin, right? Because we're going to say we're mixing these two things initially, right? And then so our change, right, is going to be hypothetically we would lose some of this, right? We would make some of that, and we would make some of that, right? Which all gets very complicated for our final math. But really, the whole point of that common ion effect says that we don't have to consider this, yes? It says that we don't have to consider that, and instead, we can just go straight into my K expression and plug stuff in, right? So we're going to plug in an X here for my hydronium ion, and we're going to just plug in 0.1 molar there, and 0.085 molar down here, and all that is going to equal 4.5 times 10 to the negative fourth. And I would solve for my x. X equals my hydronium ion concentration, which then means I would just do the negative log of that to solve for the pH. Yes, does that make sense? All right, next up, calculate the formate ion concentration and pH of a solution that is this concentration of formic acid and this concentration of nitric acid, right? And at first you're like, oh, it's the same. And then you look at it like, ooh, maybe it's not the same. So let's start by writing out the reaction like always, right? So this, right, is key here, right? So formic acid, we have HCOOH plus water, right? And that's going to give us this because that's our weak acid, because it's not one of our strong ones, right? COO minus, right? And let's think about our concentrations, right? So we have 0.05 molar formic acid, irrelevant. This, what is that? Right, that's this concentration, and that's initially 0. So we have the exact same scenario, right? So we will go ahead and set up our Ka is equal to 0.1 molar this times our X over 0.05, and then we'll solve for our x, and that will give us our hydronium ion concentration. Now, when it asks us for the pH, right, we might be tempted to try to consider the effect of formic acid, but, right, like that rule says, right, if we have formate ion, formic acid doesn't dissociate very much, yes? It dissociates even less than this 10 to the negative fourth predicts, yes? Which means that if it is in the presence of strong acid determines the pH, yes? As in for pH, I'm just going to take pH is equal to the negative log of 0.1 molar. Yes, does that make sense? Right? Which is why we always have to be mindful about what's in our solution and what matters, right? Up in this other scenario, right, all we had was a weak acid and its conjugate base, right? Down here in the second example, right, we actually have a strong acid hanging out in the solution, which is what contributes this, which is then what becomes the primary impact upon pH. Yes? All right. Thank you for listening to 17.1. Be good. Have a lovely day, and I will see you soon. Bye.